lecture. In this one, we're going to look at analog I/O programming. And hold on to your hats because this one is going to be complicated. If you don't watch this lecture 2 or 3 times, you are probably doing yourself a disservice and you're most likely missing something very important. So please plan on watching this a couple of different times and don't get frustrated if you get lost halfway through this. This is going to be a lot of information, a lot of consideration, and it is going to get a little bit hairy, so please bear with me. We are looking at the same program that we were working on in the last lecture, and we set up a ladder specifically for I/O. But now I've decided that I don't want you to have to look at my digital I/O while I'm trying to be focused on analog I/O, so I'm going to redistribute my I/O. So I'm going to come over to Program Files in our Project Navigation pane, right-click on Ladder 4 and rename it, and now it's going to be Digital I/O. And I'm going to add a new ladder, and it's going to be called Analog I/O. So now we have a ladder 6, and we're going to have to call that new ladder from the main. So we look here, and we're only calling our digital I/O. We're not calling our alarms, our controls, or our analog I/O yet. So let's go ahead and put 3 more jump subroutines in here, and we come up to our menu that is located under Program Control. So we're going to put a jump subroutine on each one of these rungs, and we're going to go ahead and call file 3, which is alarms, ladder 5, which is controls, and last but certainly not least, ladder 6, which is our analog I/O. And just as a matter of housekeeping, since we renamed ladder 4, it's only fair that we change the description here so our program is nice and coherent. And if I click on the number next to any rung, I can actually move that rung up or down in my ladder. So I'm going to move the jump subroutine command above ladder 4 just to keep them in order. That's not necessary, but it is good housekeeping in this case, and there's no reason that they need to run in a different order. So now we have a nice, clean, empty analog I/O ladder, which is being called from our main. So on runtime, the PLC is going to be examining this ladder. The first thing we need to do is add ourselves a rung or 2 or 3 or 4 that we can work with in here. And it just occurred to me, we don't have an analog module installed. So we're going to go ahead and put an analog 2 and 2 card. This has 2 channels of analog input, 2 channels of analog output. And here's your refresher course for configuration. We're going to configure all of these as 4 to 20 signals, which is typically the most common. And we're going to scale for raw proportional on one, and we're going to go ahead and scale for PID on the other one, just to spice it up a little bit. So looking at our inputs, we'll be working with raw proportional scaling on 4 to 20 milliamp. That correlates to 4,000 to 20,000 bits. And then on our outputs, we'll be looking at scaled for PID values. That correlates to a range of 0 to 16,383. Those numbers come from, of course, our last section when we were talking about bit depth and resolution. Hopefully you remember that. If not, there's a nice thing to go back and look at one more time. So now that we've got I/O defined, we've got to remember when we start programming where that module is. That's on slot number 3. So our digitals were on slot 1 and slot 2. Now our analogs are going to be on slot 3. So the first thing we're going to want to do is bring our analog signal in, and of course we typically want to scale that signal. So the first thing we're going to come to is Advanced Math, click on SCP, which is our Scale with Parameters block, and let's bring that into this rung. We're going to be addressing our input here, and that is going to be I for input, :3 for slot 3, and now instead of a slash, which means we're addressing to the bit level, we're going to put a dot or a period, which means we're addressing to a word level. So we're not looking at a 0 or 1 address. Now we're looking at something that's more complex than that. So we're going to type I:3 dot 0 for channel 0. And we're going to go ahead and have to describe this. So let's imagine that we are getting a signal in from a pressure sensor. So we're going to go ahead and label this as pressure sensor input. We won't be giving it a symbol because of course we don't refer to I/O directly. And now we need an input scale for this input. If you remember, we set our inputs up as raw proportional. So that means we have a scale of 4,000 to 20,000, which correlates to the 4 to 20 milliamp signal. So our input minimum, the lowest signal that this input can send our PLC, is 4,000. And the highest signal that it can send us is 20,000. So now we have to know what is the range of the sensor. There are pressure sensors that read 0 to 1 psi. There are pressure sensors that can read 0 to 5 psi. There are pressure sensors that can read hundreds and even thousands of pounds of pressure. In this case, we're going to imagine we have one that reads from 0 to 5 psi. Now, realize here that we are compressing 16,384 levels of resolution into a range of 0 to 5. So if we store this into an integer, we're going to have 6 levels of resolution. That can only be 0 pounds, 1, 2, 3, 4, or 5 psi. And that is not a comfortable amount of resolution for this type of process. If we're using a 0 to 5 psi pressure sensor, chances are we need to know with far more precision how much pressure that sensor is detecting. So instead of defining an integer for the output, we're going to go ahead and address a float. Now when we look to our data tables, we see that there is already a float table built in for us, and that is at location F8. So we'll go ahead and address to F8, and the software gives us the next available unused memory location, and that's F8:0. We'll take that, and that's going to be pressure. And we might even add a note in here, 0 to 5 psi. So now, anywhere this pops up, we'll see that it's not only pressure, but we'll actually see the range, just in case it helps us program down the road when we're setting different set points for the pressure. Now, we've brought our input in, we've set it equal to a float location in a data file, and now we can refer to F8:0 throughout this program if we want to know what the pressure is. We never have any reason to look all the way back to the actual input location itself. This is the most common way to scale a value, but there are certain other possibilities and considerations that can be taken at this stage. One is, what happens if somebody's actually putting a lot more pressure on that sensor than it's designed to hold? Do we ever want to read a value that's over 5 psi? Maybe we do, maybe we don't. Suppose this sensor gets disconnected, in which case we no longer have 4 milliamps coming in, we actually have 0 milliamps come in, which means our pressure reading is going to be a negative number. That negative number could very well upset our program in unpredictable ways, especially if we're running any kind of math based on the value of this pressure. So what we might do here is put in some conditional processing of that F8:0 figure, just in case, for one reason or another, our sensor is out of range. So let's go ahead and start by putting a branch into this rung and moving our scale with parameters block into that branch. So we are going to bring an LES, or less than block, into our branch, and we're going to test I:3.0, our input, and we're going to say if that input is less than 4,000, which is of course our sensor's input minimum, then we are going to use a move command, and we're going to move the minimum output of 0 to our stored pressure location of F8:0. So now there's no possible way we're going to end up with a negative pressure on F8:0. What's going to happen is when our input comes in on slot 3, channel 0, that is going to be scaled from 0 to 5. But if that input is anything less than 4,000, which would ordinarily set F8:0 at a negative value, it's immediately going to be changed on this branch, and it's going to be set to 0. And that's only going to happen if this block is true, which means I:3.0's signal coming in has to be less than 4,000. But maybe we also want a contingency for a high level. So let's go ahead and add another branch down. We're going to put in another move command, and we're going to put in a greater than instruction. So we're going to look at our I:3.0 again, only this time we're going to say, what if it's greater than its input maximum of 20,000? In that case, we're going to go ahead and move the high scaled value of 5 into our stored pressure float of F8:0. So now we are prepared for all of our contingencies. If we have a low value, we're going to keep it in range. If we have a high value, we're going to keep it in range. But we can do even more if we want. Perhaps we also want something that doesn't require all this conditional programming, but maybe we would also like to see the pressure on a scale of 0 to 100%. So we want to know, is our pressure 3.68 psi or is it 4.27 psi? But we also want to see it in terms of, is it 100% of its scale or is it 0% of its scale? So we'll go ahead and extend branch down, or better yet, why don't we go ahead and extend branch up, and we're going to put in another scale with parameters. So we've got to scroll all the way to the end, advanced math, and pull in our SCP, and we're going to scale the same I:3.0 again. We still have our same input range of 4,000 to 20,000, and this time our output scaling is going to be from 0 to 100. And that, let's say we don't need the same precision. We don't need to know if it's 72.8%. We really just need to see 73%. So in that case, we'll go ahead and store this as an integer. Again, looking over at our data files, integer table set up for us by the program, and that's N7. So let's go back to our output box and fill in N7, and it's of course prompting us for the first available memory address. We'll take 0 and we'll call that pressure again, only this time we'll put in a note 0 to 100%. So now we have multiple scaling of the same input. We have an integer and a float telling us two different representations of the same data that we can use throughout the program. And assuming that this float is sensitive to out-of-range conditions which could upset math down the road or displays down the road, we've also put in some conditional programming to handle low signals and to handle high signals. So that is just a little bit of the potential complexity of handling analog inputs. All right, one last thing before we get into the next. This is pertinent mostly to analog inputs. What we're looking at here are 4 different limits of a typical analog input signal. Those are a low level, a low level, a high level, and a high level. And when we start programming logic in the next section, it's going to be very important to understand these 4 levels and how we use them and when we need them in our program. So imagine, if you will, we have a temperature. We have an input coming in as a thermocouple, and we have an output going out to a heater. And this heater isn't controlled by a thermostat. it doesn't have variable heat. This heater is either on or it's off. And the way that we'll control this heater, we're looking at an analog signal from a thermocouple that's telling us what our temperature is. And let's imagine we have it scaled from 0 to 100 degrees. So in our program, we have a low and a high limit programmed into our control logic. When the temperature gets below 70 degrees, we turn our heater on and we latch it on so that it stays until our temperature reaches a high set point, and we'll set that high at 80 degrees. So as long as our temperature doesn't fall back down to low, our heater won't come back on, but it'll bounce, assuming that the ambient temperature is of course below our low set point. We'll say it's 60 degrees outside. Well, eventually our temperature in our system, being read by our thermocouple, is going to fall down to 70. Once the temperature falls below 70, our heater will come on, and it'll stay on until the thermocouple reads the high temperature of 80 degrees. At that time, our heater will turn off, and it'll stay off until we fall back down to our low. And that is called process control. The low and the high set points are our process control set points. They start and stop devices. As long as we are within there, that is considered our operating range. That's our process range. That's where we want our temperature to be. But sometimes things go wrong. Perhaps our heater broke. Perhaps a wire fell off. In which case, our logic is telling the heater to run. And as far as our logic knows, it can't tell that the PLC is broken. All it knows is it's energizing the output to the heater, and it should be running. When we look at our PLC, it's showing us a bit associated with the output that says, yes, the heater is on. The problem is, like any real-world appliance, sometimes they break, and when you turn it on, nothing happens. And how are we going to know that? We're going to figure that out because our heater is going to come on, but our temperature is going to keep going down. And somewhere below our low level, our process control range, we're going to have a low limit set that says whenever the heater gets down to 55 degrees, we need to sound an alarm and say we have a low temperature. And maybe we need to interrupt some part of our process which is dependent upon that temperature being within the control range. Likewise, sometimes relays stick, and generally when we're energizing an output from our PLC, that output signal is actually going to a relay which is controlling the higher voltage and or higher amperage, which is going to the actual device itself. And perhaps our output to the heater has de-energized, but the relay was stuck closed, in which case the heater, even though there was no output signal from our PLC, still had power and kept heating. And we exceed our 80 degree set point, and maybe once we get up to 90 degrees, we have a high limit set in our program that notifies the operator there's a problem, something's wrong, and again, possibly it interrupts the process, or possibly it has a way of cutting the heat somewhere upstream, maybe at a power supply that isn't dependent upon that relay for control. So this is an important concept to understand when you're programming, and it's a normal, frequently used part of process control. Sometimes you don't even need a low level. Sometimes if our temperature falls below a certain point, we just wait until it comes back up and there's no need for an alarm. Sometimes a high isn't even that important. Perhaps we have a water tank out in the middle of nowhere and the water tank has an overflow. So if the water gets too high on the tank, it just spills out into another tank which has another set of level controls. You don't always need all 4 of these, but it is important to understand when you should have an alarm condition. Sometimes it's critical, sometimes it's a safety-related issue. Other times it's just useful for an operator to know that something's out of control. Either way, this is a very critical consideration to make when you're programming a PLC.